people are asked about their life aspirations, they usually talk about wanting to change the world or make an impact. While many people have indeed made notable contributions to society, some names are better known than others. These names are often associated with significant achievements, inventions, or, in some cases, deeds of such magnitude that they are remembered. One such name is, undoubtedly, that of physicist Albert Einstein. Einstein was born in Germany in 1879 and moved to Switzerland as a young man to pursue a university education. His desire for more progressive and innovative approaches to learning led to his expulsion from school in his homeland. However, Switzerland provided him with the perfect environment to expand his intellectual horizons. He immersed himself in thinking about the nature of light and began to challenge the established laws of physics that guided the world in that era. In 1905, Einstein experienced what is currently referred to as his year of miracles. Within the course of that single year, he published 4 distinct papers that profoundly altered the scientific landscape. While each document holds significant importance, it was his third article, titled On the Electrodynamics of Moving Bodies, that left the most enduring impact on the world. This marked the inception of Einstein's special theory of relativity. Einstein's theory challenged 2 widely accepted physics theories of his time: Isaac Newton's ideas of absolute space and time, and James Clerk Maxwell's proposition that the speed of light remained constant. His papers suggested that time elapses differently depending on an individual's speed relative to someone else. This concept, now termed time dilation, asserts that a person in inertial motion will perceive time differently than another inertial individual in relative motion to the first person. To illustrate this concept more clearly, let's examine the example Einstein employed to elucidate his theory. Envision yourself on a rapidly moving train, surpassing any train speed previously achieved. As you speed past the landscape, you notice approaching a train platform where your friend eagerly awaits your passing. From both your perspectives, it seems as if you are stationary. The crucial distinction lies in your position within the swiftly moving train, while your friend remains on the platform. Now, picture this scenario. Precisely as the midpoint of the train aligns with your friend, lights at both the front and back of the train illuminate. Given the constant speed of light, and considering that both lights illuminate at an equal distance from your friend on the platform, the light from both sources would reach your friend's eyes simultaneously. Consequently, your friend would correctly perceive the lights as having illuminated simultaneously. However, an intriguing paradox arises. For you, the observer inside a fast-moving train, the situation is different. When you are on a train rushing towards the front light, it seems to you that the front light comes on first. At the same time, the tail light comes on a little later because it has to catch up with the train moving away from it. Remarkably, both points of view are correct. But how can this be the case? How can you both be right in observing the same event in different ways? Einstein's theory also brought forth the concept of length contraction. Since we understand that speed is defined as distance over time, it logically follows that for the speed of light to remain constant, the other 2 factors, distance and time, must adjust to maintain that constancy. To illustrate, consider yourself once again on the train with your friend on the platform. This time, your friend has become stronger and is now holding up a substantial canoe that spans 100 feet in length. For your friend on the platform, the canoe's length is clearly 100 feet. Its measurement is easily determined since they are stationary. Now, shift to your perspective on the train, rushing past your friend. The canoe appears significantly shorter than its actual measurement due to the high speed of your movement. Both perceptions are valid. The canoe's length remains unchanged, but its perceived length is contracted from your vantage point in the moving train. The faster your speed, the more shortened the canoe appears. While this might seem like an intriguing experiment, the speeds required for noticeable differences are not realistically attainable by humans. Einstein demonstrated that no object with mass can exceed the speed of light. As mass increases, acceleration becomes more challenging, making it impractical to achieve speeds where these effects would be observable. Therefore, experiments like the one described must be set aside. Similar to time dilation, these effects are only discernible at speeds approaching a substantial fraction of the speed of light, making them beyond the reach of everyday observations. Nevertheless, they've undergone numerous tests over the last century and remain among the most significant contributions to the field of physics in history. As mentioned earlier, 1905 is often referred to as Einstein's Year of Miracles, marked by his groundbreaking work. In that pivotal year, Einstein presented one final paper, emerging from his theory of special relativity. This paper introduced the famous equation. Equation asserts that energy is equivalent to mass multiplied by the speed of light squared. In essence, it suggests that energy and mass are interchangeable. If mass is entirely converted into energy, an immense amount of power can be unleashed. A notable example of this principle is the extraordinary power and destructiveness of an atomic bomb, where mass conversion releases energy with devastating effects. Einstein's exploration of the implications of his special theory of relativity on non-inertial frames of reference culminated in the groundbreaking publication of the General Theory of Relativity in 1915. In the General Theory of Relativity, Einstein extended his thinking to scenarios involving acceleration between frames of reference. He proposed that gravity, the force continually attracting objects toward each other, is, in reality, causing a warping or curvature of space and time. According to his findings, the larger the object, the more pronounced the curvature, since objects with mass are naturally drawn toward each other, and the one with greater mass exerts a stronger force. This concept explains the phenomenon of orbits. Planets and stars fall into the curves that their bigger counterparts create. For example, the Sun is much more massive than the Earth, and so it warps space-time much more, which grants it a larger gravitational pull. You can keep going with this idea and deduce that the whole universe exists within a system of these curves of the fabric of space-time. Isaac Newton, more than 200 years earlier, had hypothesized that an object thrown with the perfect amount of acceleration would begin to curve around our planet. With the right set of initial conditions, it could potentially remain in an endless loop, spinning around the Earth due to the force of gravity, constantly pulling it in at the perfect curve. What he was describing essentially was orbits, the exact thing that the International Space Station is doing above our heads right now. While Newton regarded acceleration and gravity as distinct forces, Einstein's theory demonstrated their interchangeability. This concept, known as the equivalence principle, posits that distinguishing between the effects of gravity and those of being in an accelerated frame of reference is impossible. An illustrative scenario involves imagining being in a windowless room. If you were to drop a ball in that room, it would fall at the rate of gravity. Now, consider dropping a ball in a rocket ship, accelerating at the exact same rate as gravity. In this case, it becomes indistinguishable whether the ball is descending due to Earth's gravitational pull, or if the floor of the rocket ship is rapidly approaching the ball because of acceleration. Einstein's general relativity, a continuation of his work, elucidated the workings of our universe. Thanks to his contributions, we can predict the trajectories of asteroids and the orbits of distant stars. Moreover, his theory finds practical application in the realm of filmmaking, where special effects engineers can precisely calculate how objects move relative to each other, even in improbable circumstances. Since the publication of Einstein's general relativity theory, numerous experiments have been conducted, affirming the accuracy of his findings. One particularly renowned confirmation came from Einstein's precise prediction that Mercury's orbit would experience a shift of 43 seconds per century due to the curvature of space-time. This prediction aligned remarkably well with observed data, showcasing the accuracy of Einstein's theory. Significantly, he succeeded in explaining a phenomenon that Newtonian mechanics, in its traditional form, could not resolve. In his later years, Einstein relocated to the United States, where he continued his work as a physicist, with a primary focus on attempting to formulate a unified field theory. Unfortunately, he did not complete this work before his death in 1955. Nevertheless, his final paper laid the foundation for future physicists to carry on his mission, aspiring to achieve a unified field theory, commonly referred to as a theory of everything. The task of reconciling both quantum mechanics and general relativity poses one of the most formidable challenges in science. Perhaps, in the not-so-distant future, we may discover the elusive master key to the universe.